Tonight, we will talk about how the moon controls the ocean. It's one of the most beautiful relationships in nature, a silent, invisible force linking the moon in the sky to the movement of waves on Earth. As you get comfortable and let your mind relax, we'll gently explore the science behind tides, gravity, and the subtle dance between Earth and its only natural satellite. This story, like the tide itself, will move slowly and calmly, helping you drift deeper into curiosity and perhaps into sleep. Let's begin at the shoreline. Have you ever noticed the ocean rising and falling throughout the day? This rhythmic movement, called the tide, is one of the oldest and most reliable cycles on Earth. It affects coastlines, ecosystems, and even human history. But what causes the tide? And why does the moon, over 200,000 miles away, have such a profound influence on the water here on Earth? To answer that, we have to start with gravity. Gravity is the invisible force that pulls objects toward one another. It's the same force that keeps your feet on the ground, the planets orbiting the sun, and the moon locked in orbit around Earth. But gravity doesn't just act locally, it stretches across space. And although the moon is much smaller than Earth, only about 1/6 its size, it still has a measurable gravitational pull. When the moon's gravity pulls on Earth, it pulls more strongly on the parts of Earth that are closer to it. Because the Earth is not a solid block, but a mixture of solids, liquids, and gases. The moon's pull creates bulges. Water, being fluid and more mobile than land, responds most noticeably. The result? Tidal bulges, raised areas in the ocean surface. One of these bulges occurs on the side of Earth facing the moon. This is where the moon's gravitational pull is strongest, and it pulls the water toward it. But there's another, more surprising bulge, one on the opposite side of Earth. That bulge is caused by inertia, the tendency of the ocean water to continue moving outward as the Earth spins. You can think of it as the water lagging behind the rotation, stretched by the centrifugal force of Earth's rotation and the moon's tug. So at any given time, there are two high tides, one on the side facing the moon and one on the opposite side. Between these high tides are two low tides. As Earth rotates, different parts of the planet move through these bulges. This is why most coastal areas experience two high tides and two low tides every 24 hours and 50 minutes, roughly the time it takes for the moon to return to the same position in the sky relative to a specific location on Earth. But this system is more dynamic than it seems. The moon is not stationary in our sky, it orbits Earth approximately every 27.3 days. And Earth doesn't just rotate, it also wobbles slightly due to the gravitational interaction with the moon and sun. These motions lead to complex tidal patterns that vary by location. Let's zoom out a bit now and consider how all of this began. The relationship between Earth and the moon was forged billions of years ago, likely during a massive collision between early Earth and a Mars-sized object named Theia. The debris from that impact eventually coalesced into the moon, and ever since the Earth and moon have been gravitationally bound. But this bond is not static. The moon is slowly moving away from Earth, about 3.8 centimeters per year, and as it does, Earth's rotation is gradually slowing. In fact, hundreds of millions of years ago, a day on Earth was only 21 hours long. As the moon pulls on Earth, it not only causes tides in the oceans, but also tidal flexing in the Earth's crust. The land itself moves slightly, almost imperceptibly, due to this gravitational interaction. The oceans respond more dramatically, but the solid Earth is not completely rigid either. Now, let's return to the ocean. Tidal forces vary based on location. Along open coasts like those on the Atlantic Ocean, the tide comes in and out relatively smoothly. but in narrow bays and estuaries, the tide can rush in like a wave, flooding large areas in a short time. One famous example is the Bay of Fundy in Canada, where the tidal range, the difference between high and low tide, can be over 50 feet. That's because the shape of the bay amplifies the natural tidal rhythm, like water sloshing in a bathtub. And not all tides are the same. Depending on the alignment of the sun, earth, and moon, we experience different kinds of tides: spring tides and neap tides. Spring tides don't have anything to do with the season. Instead, they occur when the earth, moon, and sun are aligned, during a full moon or a new moon. During these alignments, the gravitational pulls of the sun and moon combine, creating extra high tides and extra low tides. The tides seem to stretch more dramatically, as if the entire ocean is breathing a little deeper. Neap tides, on the other hand, happen when the sun and moon are at right angles relative to Earth, during the first and third quarters of the moon. Here, the gravitational forces partly cancel each other out, leading to lower high tides and higher low tides. The tidal range shrinks, and the ocean becomes more subdued. The moon's role is essential, but it's not alone. The sun also contributes to tides, about 46% as much as the moon. Its gravitational pull adds a secondary layer of complexity. Even though the sun is much farther away, its mass is so immense that it still tugs at Earth's waters. When the moon and sun work together, the effect is strong. When they compete, it softens. There's also the concept of tidal resonance. This occurs when the natural frequency of a body of water, how often it wants to slosh back and forth, matches the tidal forcing period from the moon. When this happens, tides can grow more intense. Some coastal regions experience this resonant amplification, which is why tide predictions vary so much around the globe. But tides are more than just moving water, they're also vital to life. Many marine animals rely on the tides for feeding, reproduction, and navigation. Creatures like horseshoe crabs, which have existed for hundreds of millions of years, time their mating with spring tides so that their eggs are safely deposited on high shores, away from predators. Tide pools, tiny ecosystems left behind during low tide, become temporary homes for sea stars, crabs, and anemones. The rhythm of the tide governs their entire world. For humans, tides have shaped our history too. Ancient peoples observed the moon and the tides with awe. Fishermen learned to read the sea and time their harvests based on lunar phases. Sailors understood the importance of tides in navigating harbours and coastlines. Coastal communities still rely on tide charts for everything from boating to beach going. Even today, modern scientists continue to study the moon's effect on the oceans. Satellite data helps map sea level changes, while deep-sea sensors track tidal currents that influence global climate. We're discovering how tides interact with Earth's rotation, ocean circulation, and even the melting of polar ice. The moon, then, is not just a distant rock in the sky. It's a cosmic partner. It's a silent conductor orchestrating the ceaseless motion of Earth's waters. It's a sculptor of coastlines, a guide for marine life, and a reminder that even across vast distances, gravity connects us all. And as you lie back tonight, listening to the rhythm of your breath, remember that the same forces that move the oceans are still at work. The moon, quiet and constant, continues its dance across the night sky, and the oceans respond in kind, rising and falling in a lullaby of planetary harmony. To understand how the moon truly influences our oceans, we need to look beyond the basic push and pull of gravity. The tides are not simply rising and falling masses of water, they are part of a vast, dynamic system of energy transfer. This system operates on scales that are global in size and millennia in depth, stretching back to the formation of the Earth-Moon system itself. The moon's gravitational force affects every molecule of water on Earth, but not evenly. Remember, Earth is a rotating sphere covered mostly in water, and this rotation creates complex interactions with the moon's steady gravitational pull. Because of Earth's spin and the moon's orbit, tidal bulges are not perfectly aligned with the moon above them. Instead, there is a delay, a lag between the position of the moon and the location of the high tide. This slight misalignment might seem small, but it has profound effects. That lag is caused by friction between the ocean waters and the Earth's sea floor. As Earth rotates, the ocean tries to keep pace, but the seafloor resists. This resistance causes the tidal bulges to shift slightly ahead of the moon's position. It's not just a quirk of timing, it's a transfer of energy. The Earth's rotation is gradually slowing down, and in exchange, the moon gains a bit more distance from us. That's right, our days are slowly getting longer, and the moon is spiraling ever so gently away, like a dance partner slowly backing off the stage. You might be wondering, if all this is happening on a global scale, how can it result in something as simple and predictable as the tide coming in and out twice a day? It's helpful to think of the oceans as being in constant motion, like a giant, planetary-sized pool of water. But this pool isn't still. It's stirred by gravity, influenced by the rotation of the planet, and shaped by the contours of the ocean floor, islands, and continental shelves. These features all change the way tides behave locally. For example, while the general pattern is 2 high tides and 2 low tides per day, not all places follow this exactly. Some regions experience what's called a diurnal tide, meaning 1 high tide and 1 low tide each day. Others experience semi-diurnal tides with 2 of each. And then there are mixed tides, which vary in height and timing. This variety is driven by geography. Ocean basins, coastal shelves, and undersea topography act like walls, channels, and drains in a bathtub. They alter the speed, height, and frequency of tides depending on their depth, shape, and position relative to the moon's gravitational pull. So while the moon provides the rhythm, the oceans interpret the music differently depending on where they are. Some of the most interesting effects of tides are found where water is forced into narrower and shallower regions. These are places where the tidal forces become concentrated and intensified. In narrow inlets, fjords, or estuaries, the incoming tide can cause tidal bores, a phenomenon where the tide creates a wave that travels upriver against the current. These are rare, but when they occur, they're dramatic and loud. In places like the Qiantang River in China or the Severn River in the United Kingdom, people gather just to witness this powerful surge of water flowing inland. In more open coastal regions, the effect is more gradual but no less significant. Coral reefs, for example, rely on the ebb and flow of tides for nutrient exchange. The water carries food in and waste out, maintaining the delicate balance of these underwater ecosystems. Mangrove forests, which thrive in the intertidal zone, the area between high and low tide, are equally dependent. Their roots must withstand both the force of incoming water and the exposure to air when the tide goes out. Let's take a moment to explore the intertidal zone a bit more. This is one of the most fascinating environments on the planet, and it's entirely shaped by the moon's pull. At high tide, it's submerged under seawater. At low tide, it's exposed to the air. Organisms living here have adapted to this rhythmic change, timing their activities with the lunar clock. Sea stars, barnacles, mussels, and anemones all rely on the predictability of the tides to feed, reproduce, and protect themselves. Some species have internal biological clocks, called circadian rhythms, that are synced not only to the day-night cycle, but to the tidal cycle itself. There are even creatures that follow the lunar rhythm, adjusting their behaviors with the 28-day lunar month. For example, certain species of fish and coral spawn only during the full or new moon, when tides are strongest. These rhythms are encoded in their biology, passed down over countless generations. Now let's zoom back out, this time to consider how the moon and the oceans interact with the entire Earth system. The moon's effect on the oceans doesn't stop at the water's edge. Ocean tides help regulate Earth's climate by driving large-scale ocean currents. These currents move warm water from the equator toward the poles and return cold water from the poles toward the equator. It's a process known as thermohaline circulation, or the global conveyor belt. The movement of these currents is influenced by temperature, salinity, and yes, tides. Tidal mixing occurs when tidal forces stir the ocean's layers, especially in deep water. This helps distribute heat and nutrients throughout the water column, affecting marine life and global weather patterns. Without this constant churning, Earth's climate would likely be far more extreme and less hospitable to life. You may have heard of El Niño or La Niña, weather phenomena linked to shifts in ocean temperature and circulation in the Pacific. While tides don't cause these events, they are part of the system that enables such patterns to exist. Everything is connected. The moon, the tides, the atmosphere, and the climate form a web of interaction that shapes life on Earth. And speaking of life, did you know that tides might have played a key role in the origin of life itself? Some scientists believe that life began in the shallow pools of Earth's early coastlines, where the tidal rhythm concentrated organic molecules, creating the right conditions for complex chemistry to emerge. The moon's gravitational pull may have helped stir those ancient ingredients, heating them during compression and cooling them during release. These wet-dry cycles, powered by the tides, could have sparked the first biological reactions. It's a humbling idea that every wave that rises and falls, every tide that flows in and out, is part of a process that began billions of years ago and continues to this day. The moon, circling silently above, is not just a rock in space, it's a partner in the story of life on Earth. Let's also consider human use of tides, not just in terms of history or tradition, but in energy. Tidal energy is a renewable form of power that harnesses the predictable motion of the tides to generate electricity. Unlike wind or solar energy, which can be intermittent, tides follow a consistent schedule dictated by the moon. By placing turbines in coastal areas where tides flow strongly, we can convert the kinetic energy of moving water into electrical energy. While tidal power is still a developing technology, it holds great promise for the future. Some countries, like the United Kingdom and South Korea, have already begun to tap into this source. The movement of the tides, subtle, slow, and steady, could become part of our energy solution in a changing world. Of course, tidal power isn't without challenges. The equipment must endure harsh marine environments, and not all coastal areas are suitable. There's also concern about how turbines might affect marine ecosystems. But the promise is there: a clean, consistent source of power guided by a force we've known since time began. We've come a long way from simply watching the tide roll in and out. Today, we model tides using satellite data, simulate them on supercomputers, and even incorporate them into space exploration plans. Astronauts on the moon have looked back and seen the curved Earth, covered in blue oceans, moving in harmony with the moon's gravity. And perhaps in the future, when we settle on the moon or Mars, we'll still carry with us the knowledge of how tides shaped our home. What makes this all so remarkable is that it continues quietly, day after day. The moon pulls, the oceans respond, and life moves with the rhythm. No matter where you are on Earth, whether near the sea or far inland, the moon's presence touches you. It affects the water in the oceans, the spin of the planet, and even the length of your day. It's a reminder that we are not separate from the cosmos. We are part of it. The moon and the ocean are bound together in a gravitational ballet, the force that creates waves and currents, that nourishes ecosystems and sculpts coastlines, also reminds us of our connection to the universe. Each tide is like a breath, inhaling and exhaling across the surface of the world. And as we continue this journey, exploring how the moon controls the ocean, we'll uncover more of the subtle and beautiful mechanics behind this ancient relationship. It's a story of movement, of time, of balance, and it's still unfolding beneath our feet. To understand just how deep the moon's influence on the oceans goes, we now need to explore the concept of tidal currents. While we often think of tides as vertical movements, rising and falling water levels, the truth is that tides also generate horizontal flows of water across the surface of the ocean. These are called tidal currents. They move enormous volumes of water, especially near coastlines, inlets, and estuaries. Just as the moon pulls the water toward it, creating a bulge, it also initiates a movement of water along the surface of the planet. These tidal currents occur as water tries to catch up with the gravitational pull of the moon. But because Earth is rotating, and because the water is interacting with coastlines, seafloor shapes, and even wind, the flow becomes complex. In some places, tidal currents flow smoothly in and out twice per day. In other places, especially where water is funneled through narrow channels, the currents become stronger and more erratic. Take the Strait of Gibraltar as an example. This narrow connection between the Atlantic Ocean and the Mediterranean Sea experiences powerful tidal currents that transport massive amounts of water between two very different bodies of water. The Atlantic has a strong tidal range, while the Mediterranean is more restrained. This imbalance causes constant tidal exchange, stirring nutrients and affecting marine life and water temperature. Further north, in places like the Cook Inlet in Alaska or the Pentland Firth in Scotland, tidal currents can reach astonishing speeds, up to 10 knots or more. These fast-moving flows aren't just impressive, they're a key part of the regional ecosystems. Fish and plankton depend on these currents to bring food and oxygen, while seabirds and marine mammals time their foraging with the movement of the tide. Tidal currents also create a number of unique phenomena, like eddies and whirlpools. When fast-moving tidal currents interact with underwater features like ridges or submerged rocks, they can spin into swirling patterns. One of the most famous is the Saltstraumen in Norway, considered the strongest tidal current in the world. 4 times a day, vast amounts of seawater are forced through a narrow strait, creating whirlpools and churning flows that are powerful enough to disrupt boats. Even more subtly, tidal currents contribute to the long-term mixing of the ocean's layers. This mixing process helps redistribute heat, nutrients, and salinity, all of which influence global climate and biological productivity. The ocean isn't just one large body of water, it's a system with layers of different densities, temperatures, and chemical compositions. The movement of tides helps stir this layered system, keeping it in balance. In a way, tides are like the Earth's heartbeat. Just as your heart pumps blood throughout your body, the tides move water through the ocean's arteries. They deliver nutrients to coral reefs, oxygenate shallow seas, and maintain the health of coastal wetlands. Let's talk more about those coastal wetlands. These are environments like salt marshes and mangrove forests, which exist in the liminal space between land and sea. They are among the most productive ecosystems on Earth, storing more carbon per acre than even rainforests. And they depend entirely on tides. During high tide, salt water floods into these low-lying areas, bringing with it nutrients and sediment. During low tide, the water recedes, exposing mudflats and root systems to the air. This constant flushing supports diverse species, from shellfish and fish nurseries to migratory birds that feed on tidal flats. The health of these ecosystems is tied to the regularity of the tides. When human activity disrupts natural tidal flow, through dams, levees, or coastal development, it can throw off the entire balance. Plants adapted to saline conditions may drown or dry out. Fish breeding cycles may fail. The whole web of life becomes strained. Tides even influence inland systems in surprising ways. In large river estuaries like the Amazon, the Thames, or the Mekong, the tides can push salt water far upstream. This salt intrusion alters freshwater habitats and changes the types of organisms that can survive there. Farmers and engineers have to carefully manage water use, knowing that the lunar cycle can affect their crops and water supplies even hundreds of miles inland. Now let's return to the moon for a moment, because while the moon is the primary driver of tides, its effect isn't constant. The moon's orbit is not a perfect circle, it's slightly elliptical. That means that sometimes the moon is closer to Earth, and sometimes it's farther away. When the moon is at its closest point, called perigee, its gravitational pull is stronger, and the tides are slightly higher than usual. When it's at its farthest point, called apogee, the tidal forces weaken slightly. These subtle differences lead to what are known as perigean spring tides, or sometimes colloquially as king tides. These are the highest predicted tides of the year, and in some low-lying areas, they can cause flooding even without storms or rainfall. These lunar distance changes operate on a roughly 27.5-day cycle, which combines with the phases of the moon and the sun's gravitational influence to produce a rich, repeating pattern of tidal variation. Scientists use this pattern to create tide tables, which can predict tides decades or even centuries into the future. Imagine that, using the movement of the moon to know when water will rise and fall, decades from now. It's one of the oldest and most elegant forms of natural prediction. In fact, humans have been tracking tides for thousands of years. The ancient Greeks noted the connection between the moon and tidal motion, and the Romans built tidal mills to grind grain using the power of rising and falling water. In India, sailors along the Bay of Bengal learned to navigate using knowledge of tidal flows. And in the Islamic Golden Age, scholars developed detailed astronomical tables to help predict tide cycles along major trade routes. In the 11th century, Persian polymath al-Biruni wrote about the correlation between the moon and tides. By the 17th and 18th centuries, scientists like Galileo, Newton, and Laplace began to develop the mathematical frameworks to explain tidal mechanics using physics and calculus. Newton, in particular, explained tides using his universal law of gravitation, one of the first major scientific breakthroughs to connect celestial forces with earthbound phenomena. Today, we have advanced tide gauges, GPS monitoring, and ocean buoys that constantly measure the sea surface in real time. These tools allow meteorologists and oceanographers to not only predict routine tides, but also anticipate extreme events, like storm surges during hurricanes or tsunamis triggered by underwater earthquakes. But what's especially beautiful is that even with all this technology, the core principle remains ancient and unchanged. The moon pulls on the Earth's water, and the water responds. This response happens everywhere, whether we can see it or not. Even in the deep ocean, far from any coastline, the tidal force is at work. Subtle pressure changes in the water column cause deep currents to oscillate, sometimes by just a few centimeters. These oscillations may seem minor, but over thousands of kilometers, they contribute to the movement of entire water masses, influencing climate, deep sea circulation, and nutrient cycling on a planetary scale. One of the most fascinating discoveries of recent years is the realization that deep-sea tides can cause internal waves, massive, slow-moving undulations that travel along the boundaries between layers of different densities in the ocean. These internal waves can be hundreds of meters tall and stretch across entire ocean basins, invisible to the human eye but detected by underwater instruments and satellites. They help mix the ocean vertically, redistributing heat and energy from the surface to the abyss. Again, we come back to the idea that the moon's influence is not just surface deep. It extends all the way from the sea surface to the darkest parts of the deep ocean trenches. Let's not forget the role of tides in storytelling and culture. Throughout human history, the tides have inspired myths, poetry, and folklore. In some cultures, the rising tide was seen as the breath of a sea god. In others, the moon was believed to pour water into the oceans, refilling them as it waxed and waned. Ancient mariners read the moon's face like a clock, aligning their voyages with the flow of the sea. Even today, coastal communities feel a deep connection to the rhythm of the tides. Fishermen, surfers, sailors, and divers all know to respect and understand the ocean's timing. There's a certain reverence that comes with watching the tide change, an acknowledgement that something bigger than us is at work, something predictable yet always in motion. The moon has no voice, no wind, no waves of its own. And yet, across the distance of hundreds of thousands of kilometers, it sings to the sea. Its message is gravity. Its music is the tide. And so, as we continue this quiet journey, let's remember, every time you stand by the shore and feel the water pull at your feet, you are experiencing the moon's embrace. It's not magic, it's not mystery, it's physics, but that doesn't make it any less poetic. Let's now explore what happens when the moon's influence interacts with something more unpredictable: weather. While tides are driven by the regular pull of the moon, and to a lesser extent the sun, weather is influenced by chaotic systems like temperature differences, atmospheric pressure, wind, and storms. But these two worlds, tidal forces and meteorological forces, sometimes collide, and when they do, the results can be dramatic. One of the clearest examples of this interaction is the storm surge. A storm surge occurs when strong winds and a low atmospheric pressure during a storm, especially a hurricane or cyclone, push ocean water toward the coast. If the storm arrives during high tide, especially a spring tide caused by a new or full moon, the effect is compounded. The water level can rise several meters above normal, flooding low-lying areas, overwhelming infrastructure, and altering coastlines. This happened during Hurricane Sandy in 2012. The storm struck the northeastern United States during a full moon when tides were already elevated. The combination of lunar high tide and storm surge caused devastating flooding in New York City and along the New Jersey coast. In total, the damage exceeded $70 billion. In this case, the moon wasn't causing the storm, but it was amplifying its effects. Scientists now include tidal conditions in their models for storm predictions. Knowing whether a hurricane will arrive at high tide or low tide can dramatically change the risk forecast for coastal flooding. The moon, silently circling above, becomes an important variable in disaster response planning on Earth. In contrast to the destructive potential of storm surges, the moon's influence on tidal range is a more subtle but equally important factor in long-term coastal change. Tidal range is the vertical difference between high tide and low tide. In areas with a large tidal range, such as parts of northern Canada, western France, or coastal Australia, the shoreline can shift by hundreds of meters each day. This movement doesn't just affect where the water meets the land, it also influences erosion, sediment deposition, and the formation of features like tidal flats, barrier islands, and lagoons. Over time, these tidal movements literally shape the coast. Beaches expand and shrink, dunes migrate, estuaries deepen or silt up. In regions with minimal wave energy but strong tidal flow, sediment can be carried great distances with the ebb and flow of the water. This is how features like mudflats, tidal marshes, and deltas are formed and maintained. In fact, one of the most famous examples of tidal sculpting is Mont Saint-Michel in France. This small island, crowned with a medieval abbey, sits in a bay with one of the highest tidal ranges in the world. When the tide is out, visitors can walk across sand to reach it. When the tide comes in, the island is surrounded by water, appearing to float like a castle in the sea. This transformation happens daily, driven entirely by the pull of the moon. So in a sense, the moon is a slow-moving artist, sculpting coastlines over centuries, shaping cliffs, inlets, and sands with a steady, invisible hand. Let's shift our attention now to the open sea. Even far from shore, tidal forces influence the movement of water in ways we're still learning to understand. In the open ocean, the tidal rise and fall can be only a few centimeters, barely noticeable without precise instruments. But when you add in the vast scale of the oceans, even a few centimeters of movement represents an enormous amount of water. This movement contributes to a phenomenon called tidal mixing, the stirring of ocean layers that helps maintain the ocean's vertical structure. The ocean isn't just surface water, it has layers of different temperatures and salinity, with warm, lighter water on top and cold, denser water below. Without some kind of stirring, the nutrients at the bottom would stay trapped, and surface waters would eventually become nutrient poor. Tidal mixing, driven by the pull of the moon and enhanced by interactions with underwater mountains, ridges, and continental slopes, helps circulate these nutrients upward. In doing so, it feeds plankton, tiny organisms at the base of the food chain. These plankton, in turn, support fish, whales, and eventually humans. Some of the most productive fishing grounds in the world are located where tidal currents stir nutrient-rich water to the surface. The Grand Banks off Newfoundland, the coasts of Japan, and the North Sea all benefit from this invisible force that keeps the ocean biologically rich. In recent decades, oceanographers have deployed deep-sea sensors and satellite altimeters to better understand how tides move across the globe. What they've found is astonishing. Internal tides, waves generated below the ocean's surface by the moon's gravitational pull, can span hundreds of kilometers. These internal tides roll silently beneath the waves, unseen by the human eye, but critical to the health of the planet. These discoveries are still unfolding. Tidal science, once considered an old and settled topic, is experiencing a revival thanks to advanced technology. We're realizing that the moon's influence isn't limited to shorelines, it penetrates to the very heart of ocean systems. Let's take a moment to appreciate just how vast the moon's reach really is. The average distance between the Earth and the moon is about 384,400 kilometers, or roughly 238,855 miles. That's more than 30 Earths lined up side by side. And yet from this enormous distance, the moon moves enough water to shift entire coastlines, flood estuaries, stir the deep sea, and even affect the behavior of marine animals. This speaks to the power of gravity. Gravity doesn't require direct contact. It works through space, pulling everything toward everything else. The gravitational pull between the Earth and Moon is a mutual attraction. Earth pulls on the Moon just as much as the Moon pulls on Earth. But because the oceans are fluid, they respond more visibly to this interaction. The result is a living, moving Earth shaped by forces we cannot see, but can always feel. This leads us to another intriguing idea: tidal locking. The moon always shows us the same face. You may have noticed this. Unlike the planets, which rotate visibly, the moon appears fixed, its features constant in the night sky. This is because the moon is tidally locked to Earth. Its rotation period, the time it takes to spin once on its axis, is exactly the same as the time it takes to orbit Earth. This synchronized movement is not a coincidence. It's the result of the very same tidal forces we've been discussing. Over millions of years, Earth's gravity created tidal bulges in the moon's crust. These bulges acted like handles that Earth's gravity could tug on, gradually slowing the moon's spin until it matched its orbit. Now, as the moon circles Earth, we always see the same side, the near side, while the far side remains hidden unless viewed from space. Interestingly, the Earth is not yet tidally locked to the moon, but in billions of years it could be. The same tidal forces that slowed the moon's spin are also slowing Earth's rotation and causing the moon to drift away at about 3.8 centimeters per year. If this continues, Earth could eventually rotate once for every lunar orbit, meaning that one side of Earth would always face the moon. This would have profound implications for tides. If Earth were tidally locked to the moon, the dynamic movement of the tides would largely stop. The familiar rhythm of high and low tide would flatten into a more permanent bulge of water. Coastal life, ocean mixing, and possibly even climate patterns would be altered. Thankfully, that scenario is billions of years away, far beyond the lifespan of our civilization. Still, it's worth pondering. The tides we take for granted, this rising and falling breath of the sea, are a temporary gift. They exist in this narrow window of planetary history, during a time when the moon is close enough and the Earth spins fast enough to create movement. One day, that motion may slow to stillness, and yet the moon will still be there. A silent witness in the sky, its presence recorded not just in water, but in stone. The word month comes from the word moon. Ancient calendars were based on lunar cycles. Religious festivals, agricultural seasons, and even human fertility patterns have been linked to the moon for millennia. The sea, the moon, and time itself braided together in a pattern that defines our experience of the world. And as we continue to explore this connection, we begin to see that understanding the tides is not just about understanding science. It's about understanding time, motion, balance, and the profound interconnectedness of everything on Earth and beyond it. We've talked about the tides, tidal currents, mixing layers, and even the moon's role in shaping climate and coastlines. But now, let's examine how the moon's control over the oceans impacts marine life. Not just physically, but biologically and behaviorally. Marine organisms do not just live in the ocean, they live by the ocean's rhythm. Just as our sleep is tied to the day-night cycle, the behaviors of countless sea creatures are synced with the tides, the moon phases, and the subtle gravitational influences that govern them. Let's begin with the simplest of organisms, plankton. These microscopic life forms drift in the ocean's upper layers and are the foundation of the marine food web. Many types of plankton rise to the surface at night and sink back into the depths during the day. This daily vertical migration is the largest mass movement of biomass on Earth. And although it's driven primarily by light, the tides and moon phases influence the exact timing and depth of this migration. For example, during full moons when moonlight is strong, many species of plankton dive deeper than usual to avoid predators. The moon doesn't just lift the oceans, it sets the terms of survival. Next, let's consider fish. Tidal cycles play a major role in when and where fish feed, migrate, and reproduce. In estuarine environments, fish often enter or leave in sync with the tides. Species like salmon time their return from the ocean to freshwater streams with seasonal tidal patterns. Other fish, such as bonefish or tarpon, feed actively during the turning of the tide, when prey is being swept in or out of feeding areas. Some fish even spawn in direct response to the lunar cycle. The grunion, a small fish found along the coast of California and Mexico, lays its eggs on beaches during the high tides of full and new moons. These fish literally surf the waves, spawning on sand under the cover of night and retreating before the tide leaves them stranded. 2 weeks later, as the next spring tide returns, the eggs hatch and the young are washed back to sea. It's a precise and delicate timing strategy, one that depends entirely on the moon. Then there are corals, some of the most ancient animals on Earth. Coral spawning events are among the most visually stunning displays of synchronized reproduction in the animal kingdom. Once a year, usually after a full moon and often at night, corals in massive reef systems such as the Great Barrier Reef release billions of gametes into the water in a single event. These mass spawnings are timed to the lunar calendar, ensuring that all the coral colonies in a region reproduce simultaneously, increasing the chances of successful fertilization. The moon, high in the night sky, becomes a silent conductor to this reproductive symphony. The lunar cycle affects larger creatures too, like sea turtles. Female sea turtles return to the very beaches where they were born to lay their eggs, often choosing nights near the new or full moon to dig their nests. The moon offers more than just gravity, it provides light. On moonlit nights, turtles are better able to see their surroundings, navigate the shoreline, and avoid predators. After the eggs hatch, the baby turtles also rely on the moon. They instinctively crawl toward the brightest horizon, which, under natural conditions, is the ocean reflecting moonlight. Sadly, human development and artificial lighting often confuse these hatchlings, drawing them inland toward danger. But in their natural state, these creatures are guided by the moon, a cosmic compass written into their DNA. The influence of the moon extends even deeper. In the deep sea, where sunlight never reaches, scientists have found creatures whose lives are still timed by the lunar cycle. Some deep-sea shrimp and squid rise to the surface to feed under specific moon phases, taking advantage of changing predator behavior. Even at thousands of meters below the surface, the gentle tug of the moon affects pressure gradients and internal tides, creating an invisible rhythm that life responds to. This lunar connection is not limited to animals. Certain marine plants and algae also respond to tidal and lunar cues. Some species of seaweed adjust their buoyancy in time with the tides, rising during a high tide to collect sunlight and sinking during low tide to avoid drying out. Other photosynthetic organisms regulate their internal chemical cycles with the moon's light, using it to fine-tune their growth and reproduction. There's something profound about all of this. Across the planet, in water shallow and deep, warm and cold, living things move to the rhythm of the moon. They're not calculating it. They're not looking up at the sky with telescopes. They simply feel it. The moon is not just an external object, it is a part of the living system on Earth. Now let's look at how humans too are biologically influenced by the moon, though perhaps not as obviously. For thousands of years, people have believed the moon affects our emotions, behaviors, and physical rhythms. Some of this may be folklore, but recent studies suggest there may be subtle biological effects at play. One of the most studied is the idea that the lunar cycle affects human sleep. Some research has found that during the full moon, people tend to sleep slightly less and go to bed later. Sleep quality can decline by small but measurable amounts. It's possible that this is due to the increased brightness of the moonlight, especially before the widespread use of artificial lighting. Our ancestors would have been more active on full moon nights, hunting, traveling, and socializing, simply because they could see better. There's also research into whether the lunar cycle influences hormonal patterns, particularly in women. The average menstrual cycle is around 28 days, remarkably close to the moon's cycle of 29.5 days. Some have speculated that this is more than coincidence, and that humans, like many other animals, once synchronized reproductive rhythms to the moon. In some indigenous cultures, time is still measured in moons, and fertility rites are often aligned with lunar phases. Modern science is cautious about these connections, but the interest remains. Whether or not the moon directly causes these effects, it is certainly deeply woven into our consciousness, mythology, and biological history. Beyond the body, the moon's influence shapes civilization itself. Ancient cultures across the globe used lunar calendars long before solar ones. From the Chinese and Islamic calendars to the Mayan and Babylonian systems, time was once counted in moons. Farmers planted and harvested crops based on the moon. Fishermen timed their voyages with the tides. Festivals, rituals, and ceremonies were conducted under full moons, often symbolizing renewal, transformation, or connection to the divine. The moon was not just a light in the night sky, it was a clock, a calendar, a guide, and for coastal people especially, it was an intimate force, felt in the daily breathing of the sea. Even in modern science, lunar tides are used as a tool for understanding the Earth. By analysing the way water moves in response to the moon, researchers can map the shape of the ocean floor, detect gravitational anomalies, and monitor the melting of polar ice. These observations help scientists understand everything from earthquake risk to climate change. In fact, some satellite missions, such as GRACE, Gravity Recovery and Climate Experiment, measure tiny changes in Earth's gravitational field, which includes the influence of tides. These measurements allow scientists to detect shifts in ocean mass, groundwater levels, and even the distribution of glaciers. And all of it depends, in part, on understanding how the moon's gravity moves water across the globe. It's remarkable, something as soft and subtle as a tide, just water rising and falling, can carry with it so much information about our planet's inner workings. And it's equally remarkable that this information is being read and used not just by ancient navigators or marine animals, but by orbiting satellites and supercomputers. From mythology to modern science, the moon's influence over the ocean has been a continuous thread. It is both a natural phenomenon and a source of wonder. Its pull is written into the movements of water, the behaviors of fish and coral, and perhaps even into the quiet depths of our own biology. And yet, for all that we've uncovered, the story isn't finished. There are still mysteries in how tides interact with sea ice in the polar regions, how lunar gravity might affect earthquakes or volcanic activity, and whether long-term changes in the moon's orbit could influence future climates. The moon remains, as ever, just far enough away to be out of reach, and just close enough to touch everything we know. At this point, we've seen how the moon influences tides, currents, marine life, and even aspects of human biology and civilization. But now, let's examine what happens when the moon's gravitational force interacts with the Earth's rotation and shape. Because tides are not merely about rising and falling water, they are about the way an entire spinning planet responds to an external pull. First, it's important to recognize that Earth is not a perfect sphere. It bulges slightly at the equator due to its rotation, and this bulging affects how water moves across its surface. The tidal bulges caused by the moon are not neatly centered directly under the moon. Instead, due to the Earth's rotation and the inertia of water, the bulges are offset, meaning they occur slightly ahead of the moon's position in the sky. This offset creates a powerful effect, a gravitational tug of war that actually transfers energy from the Earth to the moon. Here's how it works. As Earth spins, the tidal bulges attempt to follow the moon's gravitational pull, but they lag slightly behind due to friction with the ocean floor and coastlines. This misalignment creates a torque, a twisting force, that pulls the moon forward in its orbit. As a result, the moon gradually moves farther away from Earth. At the same time, Earth's rotation slows down. Our days are getting longer, very slowly, by about 1.7 milliseconds per century. It may not sound like much, but over billions of years, this effect adds up. When Earth first formed, a day may have lasted only 5 or 6 hours. The moon was much closer, and tides were far more extreme. This gradual exchange of energy between the Earth and moon is known as tidal acceleration, and it's one of the most fascinating examples of how interconnected celestial bodies can influence each other over vast spans of time. The moon is literally reshaping the Earth, not just by pulling at its oceans, but by altering the spin of the planet itself. We can actually see evidence of this in the fossil record. In certain ancient corals, the growth rings left behind each year show that there were once more days in a year than there are today. Hundreds of millions of years ago, there may have been 400 days in a year. The moon's gradual drift has stretched those days out, reducing their number but increasing their length. This slow dance between Earth and moon continues today, silently, shaping the conditions of life. Now let's explore how this energy exchange contributes to Earth's stability. The moon does more than raise tides. It helps stabilize Earth's axial tilt, the angle at which the planet rotates relative to its orbit around the Sun. This tilt, currently about 23.5 degrees, is responsible for our seasons. Without the moon, Earth's tilt could wobble chaotically over time, leading to extreme shifts in climate. Why? Because Earth is slightly ablate, not a perfect sphere, and its bulging equator interacts with gravitational forces from the moon, sun, and even other planets. The moon's mass and its proximity act like a stabilizing counterweight, reducing the degree to which the tilt can vary. Simulations suggest that without the moon, Earth's tilt might fluctuate wildly, swinging from nearly no tilt, eliminating seasons altogether, to more than 85 degrees, causing the poles to point directly at the sun for long periods. These dramatic swings could make Earth's climate unstable, possibly rendering large parts of the planet uninhabitable for long stretches of time. In this way, the moon, through tidal forces and gravitational stabilization, has been a quiet guardian of Earth's habitability. It's hard to overstate how important this is. While many planets and moons have liquid water, few show the level of stability and long-term climate moderation that Earth does. The moon's role in creating regular tides and maintaining axial balance may have been critical for the development and persistence of complex life. Let's now return to the surface and talk about a concept that is often misunderstood: why we experience 2 tides per day when the moon orbits Earth only once every 27.3 days. This brings us to a key point about the physics of tides: the centrifugal force created by the Earth-Moon system. As the moon orbits Earth, the two bodies actually revolve around a shared center of mass called the barycenter. This point isn't at the center of Earth. It's located about 1,700 kilometers beneath Earth's surface, on the side facing the moon. Earth and the moon both orbit this shared point. Because of this motion, there is an outward centrifugal force experienced on the side of Earth opposite the moon. This force counterbalances the moon's gravitational pull on the near side. As a result, 2 tidal bulges form, one on the side facing the moon, due to gravity, and one on the far side, due to centrifugal force. As Earth rotates, different regions pass through these bulges, creating 2 high tides and 2 low tides each day. It's a beautiful, symmetrical system, gravity pulling from one side, momentum pushing from the other. Earth spins beneath this system, and the oceans rise and fall in rhythm. Now, let's examine how geography disrupts this neat pattern. On a planet entirely covered in water, with no land masses or friction, tides would follow a regular, almost perfect cycle. But Earth's continents, coastlines, and underwater features dramatically affect tidal patterns. Bays, gulfs, islands, and continental shelves interfere with tidal waves, causing reflections, amplifications, and delays. In some places, this interference creates resonant tides, where the natural frequency of a coastal basin aligns with the tidal forcing frequency, amplifying the effect. The Bay of Fundy in Canada is one of the most famous examples. There, the difference between high and low tide can exceed 16 meters, over 50 feet, due to this resonance. These extreme tidal ranges shape the land and local ecology. At low tide, vast mudflats and seaweed beds are exposed, attracting birds and marine life. At high tide, the entire landscape transforms into open sea, and it all happens twice a day, like clockwork, under the moon's steady gaze. On the other hand, in locations where local geography dampens the tide, the range may be just a few centimeters. In some parts of the Mediterranean Sea, for instance, the tidal difference is minimal. Not because the moon's pull is weaker there, but because the shape of the basin disperses the energy. Even underwater mountain ranges like the Mid-Atlantic Ridge play a role in how tides move. These features can break up tidal waves into smaller components or generate internal tides that move along the boundaries of ocean layers. Some of this energy is dissipated as heat. Some is transferred into currents. All of it contributes to the planet's dynamic ocean system. Tides also have a direct impact on coastal infrastructure and city planning. In regions prone to flooding, tide levels must be accounted for in the design of ports, drainage systems, seawalls, and bridges. Engineers use precise tide predictions when building canals and tunnels. For instance, the construction of the Thames Barrier in London was based on careful analysis of both historical tides and future projections, allowing the city to protect itself from tidal surges made worse by storms and rising sea levels. In some cities like Venice, Italy, tidal flooding, or aqua alta, is a regular event. Efforts to mitigate this, such as the Mose project, a series of mobile gates that block high tides, rely on an intimate understanding of how the moon, wind, and atmospheric pressure combine to raise sea levels. Tides affect commerce, fishing, navigation, and even tourism. Beachgoers time their visits with low tide to explore tide pools. Surfers seek specific tidal phases for ideal waves. Ships schedule their departures and arrivals with the tides to ensure enough water depth in harbours. Even in the digital age, the ancient rhythm of the tide remains essential. In a way, the moon has become a collaborator in our society's most basic rhythms. It governs the way fishers cast their nets, how cities defend themselves, and when ships leave port. The moon, through its silent pull, has become woven into our routines without ever saying a word. And now, as sea levels rise due to climate change, understanding the moon's influence is becoming more important than ever. Coastal communities around the world face new challenges. What was once a normal high tide can now become a flood event when combined with sea level rise and weather extremes. Scientists call this nuisance flooding, when streets, sidewalks, and storm drains overflow during otherwise routine high tides. These events are increasing in frequency and severity. Tide gauges from around the world show that these minor floods, once rare, are becoming regular occurrences. And while the moon hasn't changed, the baseline ocean it pulls on has risen. The moon still moves the water in the same way, but now the water is closer to the edge. As we continue exploring the moon's control over the ocean, let's turn our attention to a force that is subtle yet powerful: tidal energy. The tides, driven by the moon, are one of the most predictable and renewable sources of energy on Earth. Unlike solar or wind power, which depend on weather conditions or daylight, tidal energy follows a constant lunar rhythm. Twice a day, every day, the moon raises and lowers billions of tons of seawater with exquisite reliability. Harnessing this movement for human use has long been a dream, and in recent decades, it's become a reality. Let's start with the basics. Tidal energy can be captured in two main ways: tidal range systems and tidal stream systems. Tidal range systems operate much like a dam. A barrier or barrage is built across a tidal estuary or bay. As the tide comes in, water builds up behind the barrier. At high tide, gates are closed. Then, as the tide begins to fall, the gates are opened and the trapped water flows back out through turbines, generating electricity, similar to a hydroelectric dam. The most famous example of this is the Reims tidal power station in France, built in the 1960s. It uses the tidal range of the Reims River estuary, where the difference between high and low tide can exceed 13 meters. The station produces enough electricity to power tens of thousands of homes. But while tidal barrages are effective, they can be environmentally disruptive, altering estuarine ecosystems, changing sediment flows, and impacting marine life. That's why much of the recent innovation in tidal energy has focused on tidal stream systems. These work more like underwater wind turbines. Instead of capturing the vertical rise and fall of tides, they capture the horizontal flow, the powerful tidal currents that rush through straits and channels. Imagine a series of turbines anchored to the sea floor, spinning as the tide flows in and out. These can be placed in areas with strong natural tidal flows, such as Scotland's Pentland Firth, Canada's Bay of Fundy, or the coasts of South Korea. The advantage of tidal stream systems is that they don't require large dams or alterations to the coastline, and they generate power on both the incoming and outgoing tides. Some modern prototypes even use floating platforms with turbines suspended beneath, drifting slightly with the flow but anchored securely to the seabed. The promise of tidal energy lies not just in its renewability, but in its predictability. We can forecast tides centuries in advance. That makes tidal power far more stable than solar or wind, which vary with cloud cover and atmospheric conditions. But of course, challenges remain. Seawater is harsh, it corrodes metal, wears down blades, and requires durable, marine-grade materials. Installing and maintaining turbines underwater, often in remote or turbulent locations, is costly and technically demanding. The energy captured from tides is modest compared to the vast energy needs of modern cities, though it can still provide crucial power to coastal communities and islands. Still, as technology improves, many countries are looking again to the moon as an indirect source of power. The gravitational pull that raises the sea each day may one day light our homes. In fact, the moon has been a source of mechanical energy for centuries, even before electricity. As early as the Middle Ages, humans used tidal mills to grind grain. These simple machines operated in tidal estuaries, where water would flow into a pond or basin at high tide through a one-way gate. When the tide retreated, the stored water would be released, turning a water wheel and powering a millstone. Some of these mills still exist today as historical landmarks, reminders that long before satellites or smartphones, people were already tapping into the rhythm of the moon. But the moon doesn't just drive energy, it drives navigation. For as long as humans have sailed the seas, tides have shaped where, when, and how ships could move. In harbours and shallow waterways, knowing the tides is essential for safe passage. A ship that attempts to enter port at low tide may run aground. Sailors have always studied tide tables, watched the moon, and used the alignment of the sun and moon to anticipate water depth. In some ports, like Liverpool or Rotterdam, large commercial vessels must time their arrival to coincide with high tide in order to reach the dock. Even today, massive cargo ships crossing the globe rely on precise tidal forecasts. Pilots who guide ships into harbours are trained to read tidal currents as skillfully as they read maps. A few centimetres of extra depth, or a few knots of current, can mean the difference between safe passage and serious trouble. In rivers, especially those close to the ocean, tidal bores are a spectacular and challenging phenomenon for navigation. A tidal bore occurs when the incoming tide travels up a narrowing river and forms a wave, or series of waves, that rush upstream against the current. The Amazon River has a famous tidal bore known as the Pororoca, which can travel at speeds up to 25 kilometers per hour and reach several meters high. Surfers have ridden this wave for miles inland, but for boats it can be dangerous. Navigation in such waters requires not just technical skill, but a deep understanding of lunar timing and tidal physics. This brings us to another important aspect of tides: their role in timekeeping. Before mechanical clocks, the passage of time was often measured by the tides. Coastal communities used the sea's rise and fall to structure their daily lives. Fishermen went out with the tide and returned with it. Ferries operated only at high tide. Families knew when it was safe to cross tidal flats or gather shellfish. Even today, tidal time is marked on nautical charts and coastal maps. Sailors and beachgoers alike plan their activities around it. In many places, tidal bells are installed to chime at high or low tide, reminding everyone in earshot that the sea is shifting and time is moving forward. And here's something you might not expect. Tidal cycles even shape national boundaries. The line between land and sea is not fixed. In many countries, legal coastlines are defined by the mean high water mark. The average high tide line over a 19-year cycle, known as the metonic cycle. This lunar-based system is used to determine public versus private land, jurisdiction over coastal zones, and the placement of infrastructure. When tides shift, land is gained or lost. A storm surge may temporarily push the tide inland. Long-term sea level rise may permanently alter the high tide line, changing legal maps and land ownership. In this way, the moon has a subtle hand in the drawing of human borders. Tides also intersect with ecological management. In coastal ecosystems, such as salt marshes, estuaries, and mudflats, conservation efforts must account for tidal flows. Wetlands need to flood and drain regularly to support their unique plant and animal life. Restoring or protecting these areas often involves restoring natural tidal rhythms. For example, if a seawall or levee blocks the tide from reaching a marsh, the ecosystem begins to collapse. Salinity drops. Fish can no longer spawn. Birds lose feeding grounds. Restoring the tidal connection can bring an area back to life within months. In environmental science, tidal restoration is one of the most effective tools for reviving degraded coastal systems. And the moon, though it doesn't directly participate in these projects, is the essential partner, providing the pulse, the motion, the reliable force that keeps these systems functioning. This concept even applies to urban planning in coastal cities. As climate change accelerates, engineers are designing buildings and infrastructure that account not only for rising seas, but for tidal behaviour. Flood-resistant buildings now consider not just worst-case rainfall, but lunar high tides, king tides, and tidal surges. Some architects are creating amphibious houses that float during high tide and rest on land during low tide. Floating docks, tidal gardens, and tidal plazas, public spaces that intentionally flood and drain, are emerging in forward-thinking cities like Rotterdam and Singapore. We are learning not to fight the tide, but to move with it. In a way, that's what humanity has always done. Whether in science, engineering, or myth, the tide teaches us the value of rhythm, flexibility, and respect for forces larger than ourselves. We live in a tidal world, not just physically, but metaphorically. Life ebbs and flows. Challenges rise and fall. The moon reminds us that what seems like a force beyond our control can also be a guide, a pattern, a source of renewal. The tides may be one of the most ancient and predictable forces on Earth, but they continue to shape the most modern parts of our lives. And all of it, every boat, every harbour, every power station, every wave in the surf, moves to the silent pull of the moon. By now, we've seen that the moon's influence on Earth is far more than poetic. It's physical, measurable, and dynamic. It moves the oceans, shapes the coastlines, guides marine life, and even informs human infrastructure and energy production. But as we go further, we begin to ask more complex questions. How stable is this system? How might it change over time? And what happens if the moon, this constant partner in Earth's motion, keeps drifting away? Let's start with what we know for certain. The moon is slowly receding from Earth. Every year, it moves about 3.8 centimeters farther away, roughly the rate at which your fingernails grow. This retreat is due to the same tidal friction we discussed earlier. As Earth's rotation pushes the ocean bulges slightly ahead of the moon's position, energy is transferred from Earth's spin into the moon's orbit, causing it to spiral outward. It may seem like a small effect, but over millions and billions of years, it adds up. When the moon first formed, around 4.5 billion years ago, it was much closer, possibly only 20,000 to 30,000 kilometers away, compared to its current average distance of 384,400 kilometers. At that time, the tides would have been immense, with waves hundreds of feet tall, crashing across primitive coastlines every few hours. The young Earth would have spun much faster, with days lasting only 5 to 10 hours. Over time, the moon pulled on Earth's spin, lengthening the day and calming the tides. What began as a chaotic system evolved into a more gentle rhythm, creating the stable, moderate environment that allowed life to develop and thrive. Now, fast forward into the far future. As the moon continues to drift away, its gravitational influence will gradually weaken. This will lead to smaller tidal ranges, lower tidal energy, and eventually slower oceanic mixing. The tides won't disappear, but they'll become more subtle, less powerful over long time scales. At the same time, Earth's rotation will continue to slow. Eventually, Earth could become tidally locked to the moon, meaning one side of Earth would always face the moon, just as the moon always shows us the same face today. In that distant era, Earth's day would match the moon's orbital period, about 47 days based on current projections. Of course, this will take billions of years, and other cosmic events, like the expansion of the sun, may intervene before it ever happens. But it illustrates how even celestial rhythms that feel eternal are, in fact, evolving. Let's come back to the present and talk about how scientists study tides today. Tidal science is not just ancient knowledge passed down by seafarers. It's a modern, data-driven field that combines astronomy, oceanography, mathematics, and satellite observation. Tide predictions rely on harmonic analysis, a mathematical method that breaks down tidal patterns into dozens, or even hundreds, of sine waves called constituents. Each constituent corresponds to a specific astronomical influence. The moon's position, its distance from Earth, its angle relative to the equator, and the influence of the sun, among others. The two most important constituents are M2, the principal lunar semi-diurnal tide, which completes a cycle every 12 hours and 25 minutes. S2, the solar semi-diurnal tide, with a cycle of exactly 12 hours. These two waves interact to create spring and neap tides depending on how they align. Spring tides occur when the moon and sun's gravitational forces combine during full and new moons, creating higher highs and lower lows. Neap tides happen during the first and third quarters of the moon, when their forces partially cancel out. But that's just the beginning. There are dozens of smaller constituents, some with strange names. N2, K1, O1, L2, each adding complexity to the tide's behavior in any given location. Tidal data is collected from a network of tide gauges installed in harbours and coastal stations around the world. These instruments record water levels in real time, often down to the millimetre, providing the historical record needed to calculate accurate predictions. Some records go back over a century, revealing how tides are changing with shifts in sea level and coastal development. In the last few decades, satellites have added a powerful new perspective. Missions like TOPEX, Poseidon, Jason 123, and the Sentinel series have used radar altimetry to measure ocean height from orbit. These satellites can detect not just surface tides, but internal tides, subsurface waves that travel along layers of density deep beneath the ocean surface, invisible to the naked eye. By studying the global tides from space, scientists are learning how the moon's pull affects ocean heat transport, nutrient cycling, and even the behavior of the climate system. Let's talk briefly about internal tides, because they're one of the moon's most mysterious influences. Internal tides form when tidal currents encounter underwater features like seamounts, ridges, or continental slopes. These features disturb the stratified layers of ocean water, creating waves that move not along the surface, but within the ocean itself, sometimes traveling thousands of kilometers before dissipating. These hidden waves are important for several reasons. First, they mix cold, deep water with warmer surface water, helping to regulate ocean temperature. Second, they bring nutrients from the deep up to sunlit layers, supporting marine ecosystems. And third, they may influence global ocean circulation patterns like the thermohaline conveyor belt, which plays a major role in Earth's climate. And once again, it all begins with the moon, a satellite in the night sky, lifting the oceans, stirring the depths, and shaping invisible waves beneath the surface of the sea. Now let's shift to something more human, how cultures throughout history have interpreted the moon's effect on water. Long before the physics of gravity was understood, people observed the moon's connection to the tides. Ancient sailors, farmers, and priests noticed that the ocean rose and fell in time with the moon's phases. They may not have known the mechanics, but they saw the pattern. In many mythologies, the moon was associated with water, fertility, emotion, and change. In Greek mythology, the goddess Selene drove her chariot across the night sky, bringing with her the tides and the rhythms of the sea. In Hindu cosmology, the moon god Chandra is considered a nurturer, linked to the flow of sap in plants, blood in animals, and tides in the ocean. The Maori of New Zealand used lunar calendars to time their fishing expeditions, believing certain moon phases brought more abundant catches. In many coastal indigenous cultures, people lived by the lunar tide clock, not a 24-hour cycle, but a 12.4-hour rhythm, which governed when to fish, when to gather shellfish, and when to travel by water. Some even carved tide cycles into wood or stone, using symbols to track the moon's influence. Even the word lunatic comes from the belief that the full moon affects human behavior, a notion that, while not strongly supported by science, persists in the popular imagination. There is something deeply intuitive about the connection between the moon and water. The moon pulls the oceans. Our bodies are mostly water. Is it so strange that we might feel the tug too? This leads us to consider how tides shape our sense of time, space, and place. Unlike the abstract ticking of a clock, the tide is tangible. It flows under your feet. It moves the boats in the harbour. It leaves lines of seaweed on the sand. It's a kind of breathing that you can measure, not in seconds or minutes, but in motion and depth. Tide charts, which once hung in lighthouses and shipping offices, are now apps on our phones. Surfers check tide conditions before paddling out. Divers plan trips around slack tide when currents are calmest. Kayakers, sailors, and clammers do the same. But while the tools have changed, the knowledge is ancient. To understand the tide is to understand how the moon and earth dance together, how distant forces shape local realities. The very concept of shoreline is not a fixed point, but a moving boundary. Each day, the ocean reclaims and then releases the land in a gesture as old as the planet itself. And this moving boundary is full of life. Tide pools bloom and drain. Crabs scuttle between rocks. Mussels clamp shut as the water retreats. Seaweed drapes over stones like curtains drawn with the moon. Children chase waves and build castles just out of reach. It's a world in motion, gentle, powerful, and governed from above. So when we say the moon controls the ocean, we are saying something both literal and poetic. Yes, it's physics, gravity, rotation, orbital dynamics, but it's also rhythm, pattern, presence. The moon gives the ocean its breath, and in turn, the ocean shapes the world. As we near the end of our journey, the question becomes not just how the moon controls the ocean, but how this relationship might evolve in the future, and what it means for life on a changing planet. Let's begin with something both practical and profound: climate change. The moon's gravitational pull has been a constant force for billions of years, but the ocean it pulls on is no longer the same. Earth's average sea level is rising, and this changes the dynamics of how tidal forces play out along coastlines. Higher sea levels mean tides reach farther inland. In low-lying areas, the same gravitational pull now results in more frequent flooding. What used to be a high tide becomes a damaging event, especially when paired with storm surges, heavy rain, or onshore winds. This is sometimes called sunny day flooding, when seawater rises onto streets and sidewalks during a perfectly calm day, simply because the tide is unusually high. These events are increasing in cities like Miami, Norfolk, Jakarta, and Venice, not because the moon has changed, but because the baseline sea level has. The lunar cycle still governs the rhythm, but now the entire ocean is a few inches, or in some places, a few feet, closer to human infrastructure. Climate scientists are now factoring tides into flood risk models, urban planning, and emergency response systems. When a full moon coincides with a storm and rising seas, the effects can be devastating. We saw this with Superstorm Sandy in 2012. It made landfall during a spring tide, amplifying the storm surge and contributing to widespread destruction in New York and New Jersey. This is where our understanding of lunar tides becomes more than theoretical. It becomes a tool for adaptation and resilience. Engineers, policymakers, and coastal communities are learning to work with the tide, not against it. Some are restoring natural buffers like wetlands and mangroves that absorb tidal energy. Others are building floating neighborhoods or elevated roadways. All of it starts with understanding where the water moves, and when, and why. And that story always leads back to the moon. But tides are not only rising, they are also changing in complexity. In many parts of the world, scientists have detected subtle shifts in tidal amplitude and timing. Some of this is due to changes in the moon's orbit, but much of it relates to the redistribution of water across the planet. Melting glaciers, ice sheets, and changes in ocean circulation. When masses move from land to ocean, Earth's moment of inertia shifts. This affects rotation speed and the tilt of the axis. These changes, in turn, alter how the moon's gravity interacts with different parts of the globe. It's a feedback loop that sounds almost too grand to believe. The moon pulls on the ocean warms and rises. The distribution of that water alters how the moon's pull is felt. Even small variations in mass or motion can ripple out across the entire system. This kind of change also affects Earth's wobble, known as axial precession, a slow, cyclical shift in the orientation of our Earth's spin axis. Over thousands of years, this wobble changes the angle and intensity of solar radiation hitting different latitudes. That affects climate patterns, glaciation cycles, and the distribution of ecosystems. The moon plays a stabilizing role in all of this. It acts as a gravitational anchor, damping the extremes of axial wobble and helping to maintain a relatively stable climate. So the moon doesn't just pull on the oceans, it helps keep Earth itself balanced, like a keel on a ship. Let's zoom back in now to something we can observe more immediately: the ecological importance of the intertidal zone. This is the area between high and low tide, where land and sea trade places twice a day. It is one of the most dynamic and productive environments on the planet, and it only exists because of the moon. In the intertidal zone, organisms must adapt to extremes: submerged 1 hour, exposed the next. Sunlight, dryness, salinity, and temperature all fluctuate wildly. Yet despite this, or perhaps because of it, this zone teems with life. Here you'll find barnacles clinging to rocks, feeding when submerged, anemones opening their tentacles when the tide rolls in, sea stars hunting mollusks in the shallow pools, algae and kelp anchored in place, swaying with each pulse of the moon's pull. Predators come and go with the tide, birds during the low, fish during the high. Crabs scurry between crevices, mussels filter nutrients from the water, and each tide brings a fresh infusion of oxygen, plankton, and detritus. It's a living clock, ticking with the lunar beat. These environments are also nurseries. Many marine species lay their eggs in shallow tidal pools or estuaries, where the dynamic conditions protect them from open ocean predators. Juvenile fish, shrimp, and shellfish grow up here before migrating to deeper waters. Yet these fragile ecosystems are vulnerable. Coastal development, pollution, and sea level rise threaten their balance. Protecting them means preserving not just a patch of coastline, but an entire lunar system of life. In recent years, scientists and artists alike have turned to the tides for inspiration. Some research projects use biological clocks to track how animals respond to tidal cues at the genetic level. Others study how microplastic pollution moves in and out with the tides, using it to map contamination patterns. And in a more creative realm, artists have created tidal sculptures, installations placed at the shoreline that are revealed or hidden depending on the tide. These works remind viewers of the hidden forces moving just beneath the surface of daily life. One moment, a statue appears to walk on water. The next, it's submerged beneath the moon's command. Let's pause for a moment and consider how rare all of this is. Among all the planets in our solar system, Earth is the only one with liquid surface oceans and a large, proportionally sized moon. This combination creates unique tidal forces. While other moons may have subsurface oceans, like Europa or Enceladus, their interactions are vastly different. Tides there are internal, icy, and driven by interactions with gas giants. Here on Earth, we have visible tides, surface tides, life-driven tides. all under an atmosphere that allows us to breathe and watch the sky. This is no ordinary arrangement. The moon is not just a feature of Earth, it's part of Earth's system, an essential piece of its rhythm, stability, and biology. Some scientists suggest that without the moon, life on Earth, particularly complex life, might never have evolved. The moon created regular, shallow environments that fluctuated in time with the tides, promoting evolutionary pressure. It shaped climate, kept the poles from tipping too far, and may have helped spark early migrations from sea to land. And it continues to shape evolution even today. Species adapt to tidal cues. Generations are timed with lunar phases. Behavioral patterns from fish schooling to coral spawning are etched into the DNA of marine organisms. The moon isn't just a background actor in this story, it is a co-author of life's script. So when we look up at the night sky and see the moon glowing above the waves, we're not just seeing a distant sphere of rock, we're seeing a partner, a force, a companion in the ancient, ongoing motion of the Earth's oceans. The moon doesn't just reflect sunlight, it reflects a deeper connection between space and sea, gravity and biology, motion and time. And the ocean, in turn, reflects the moon, not just on its surface, but in its deepest flows. We've traced the moon's influence from the rise and fall of water along every coast on Earth, to the migration of fish and the blooming of plankton, to the shaping of coastlines and the rhythms of coral spawning, to the design of human cities and the power grids that light them, all the way to the long-term stability of Earth's tilt, rotation, and habitability. What began as a gravitational pull becomes something much larger, an elegant web of relationships between rock and water, sky and sea, motion and life. The moon, our quiet companion in space, never stops pulling, and the Earth, covered in oceans, never stops responding. We often think of the moon as distant, silent, a cold, white sphere hanging in the night sky. But after everything we've discovered, it's clear. The moon is anything but passive. It is active. It is essential. It is in constant conversation with our planet, writing a pattern that plays out not in hours or days, but across billions of years. This rhythm, this steady pulse between moon and ocean, is not just beautiful, it's stabilizing. In a universe full of chaos, collision, and randomness, the moon gives Earth something precious: predictability. Twice a day, the ocean rises and falls. Once a month, the tides surge and recede with the full and new moons. Once every 18.6 years, the lunar nodal cycle modulates high tides around the globe. These layers of rhythm make life not just possible, but sustainable. They create margins, shorelines, breathing spaces. They give time to adapt, evolve, and grow. And they continue uninterrupted, regardless of whether we notice them or not. That's the quiet power of the moon. It doesn't demand our attention, but it rewards our curiosity. Because to study the moon's control over the ocean is to glimpse the grand mechanics of our world in action. It's to understand that nothing on Earth, no wave, no breeze, no heartbeat, exists in complete isolation. All things are connected, often in ways invisible to the eye. The tides remind us that change is constant but patterned, rising, falling, ebbing, flowing. There is movement, but there is also return. And that rhythm can be comforting. Even as sea levels shift and climates change, the moon remains, orbiting above, pulling the waters forward. Even in times of uncertainty, the tide still comes in. The tide still goes out. Each wave is the moon's whisper. Each high tide, a gentle reminder that we live within a system, vast, beautiful, and responsive. For those who live near the coast, the sound of the tide is the sound of home. For those far inland, it's a pull we can feel in our bones, if not our ears. We are water, we are motion, we are tied quite literally to the moon. And so, as you close your eyes tonight, know that the ocean is moving. Somewhere, waves are curling in. Beaches are being slowly washed. Deep currents are shifting under moonlight. It's all still happening, silently, faithfully, whether we're awake or at rest.
The moon continues its orbit, the tides follow, and the world breathes over and over again.
So tonight, let the steady rhythm of the moon and the sea rock you gently into sleep. And remember, the next time you stand on a shore and watch the water rise around your feet, you're watching the moon in motion. Good night from all of us here at Soft Science, and thank you for spending this time with the tides.